let's talk about automatic control of mechanical ventilation. And Jason Bates is certainly going to present something.
All right. I'm going to try and give an overview of the issue of automatic control of mechanical ventilation, and this is a general problem in the general problem of closed-loop control. So let's just consider what the general nature of the problem is, because closed-loop control is a very widely found engineering paradigm in all sorts of areas. In fact, everybody in this room, I hope, is currently engaged in the automatic control of ventilation, and it involves three components. Okay, so we've got the sensors, the controller, and the effectors. Now, the sensors are, if you go to the next slide, the sensors and the natural control of ventilation are the chemoreceptors and the mechanoreceptors predominantly. And they are giving the controller, which is the central pattern generator for most of the time, unless you care to occasionally override it by conscious control, but the central pattern generator is receiving information from these sensors about how the effectors, namely the respiratory muscles, are doing. So if the muscles are doing their job properly, the sensors are picking up that information, telling the brain, keep doing what you're doing. If there needs to be a change due to the onset of exercise or whatever, the sensors will pick that up and tell the effectors to alter their course of action accordingly. So we've got this feedback loop going round and round here. Engineers sometimes call this servo control. Now, in the case of mechanical ventilation, the standard scenario clinically is that many of those components get replaced by other things. In the case of the sensor, if you have a patient who's really not able to breathe at all, their own chemo and mechanoreceptors are replaced by the physician's clinical acumen and some medical devices, maybe an O2 sat monitor or some measure of tidal volume or carbon dioxide or something. The controller gets taken over by the physician. So the physician's brain, in a sense, replaces that of the patient. The physician starts making the decisions. And the effectors are now replaced by a mechanical ventilator. So this is a very unnatural situation, but it's the one that usually pertains in the clinic. And it's still automatic control of ventilation. It's just not a very rapidly responding situation. And what we're interested in doing is seeing whether we can make it better by some kind of automated control. Now, how might we do that? Well, one possibility is to replace all those sensors completely with medical devices. So we take the physician out of this particular picture and we use monitors on oxygenation, carbon dioxide production, maybe, I don't know, some sensor of patient movement perhaps. And we replace the controller now with a computer algorithm which goes to direct a mechanical ventilator. And I'm going to say a novel mechanical ventilator here because most standard mechanical ventilators are not set up to do this. So now what we've done is we've taken the physician completely out of this loop. So the physician is now unemployed. But you'll be relieved to hear that that's not going to happen anytime soon at the current rate of progress. This is still very much something that's on the drawing board, although some attempts have been made, and I'll describe briefly the nature of those attempts. Now, we've heard about proportional assist ventilation already, so I don't need to say too much about it, but as it's conventionally conceived, it's an example of open-loop control, where the physician sets the parameters of the ventilation, and it just goes off and does its thing without getting any feedback from the patient on how it's doing. And the way proportional assist control works is if this equation here represents what's going on in the patient's respiratory system, where the pressure required to inflate the lungs is now the resistance of the lungs times the flow plus the volume going into the lungs divided by the compliance, possibly plus some offset pressure, then what the proportional assist ventilator seeks to do is take out some fraction of that equation and hand it over to the machine. So if the pressure applied by the ventilator is now some constant times the flow plus another constant times the volume, and I've written these constants as alpha times R and beta divided by C, where alpha and beta have got to be less than 1. That's important. If they're bigger than 1, the machine will run away with itself. Then what you have is now the servo piston of the proportional assist ventilator, which is driven by this particular pressure algorithm on the basis of measurements of pressure and flow, ventilates the patient. Now, what would be nice, which would make proportional assist a truly closed-loop automatic controller ventilator, would be if we could track changes in resistance and elastance in the patient and modify these alpha and beta parameters accordingly. So if you have a patient on a ventilator who's maybe getting better or getting worse and their resistance and compliance or elastance, as I've got here, are changing, it would be nice to have the ventilator responding automatically, and then you really would be having a servo control feedback loop operating here. Now, the conventional proportional assist ventilators, fortunately, not able to do that very easily, because the very signals that it uses in order to drive the ventilator are the same signals that are required to measure R&E, and you can't do the two things at once. So this loop, that's why I have this little X here, this loop is not closed in the conventional concept of proportional assist. The next speaker, I'm sure, is going to tell you a novel way in which that can be done, so I won't say any more about that. Let's talk about medical devices as sensors, because this is an important thing. And if we are going to have automatic control of ventilation, we've got to have some machines that are sensing what's going on and feeding back relevant information to a computer algorithm. So obviously you have pulse oximetry, which could give you arterial oxygen saturation. You could have real-time gas analysis at the endotracheal tube, measuring in particular something like end-tidal PCO2. And you can have airway pressure, obviously, as a measure of when you should terminate the breath. Esophageal manometry would be another very useful, somewhat more invasive technique to use so that you could measure esophageal pressure, because really when you're talking about ventilating the lung, it's the pressure across the lung that you want. So you need to have the difference between airway opening pressure and esophageal pressure. Yeah, there you are, to get transpulmonary pressure. And as I've said, I won't say any more about this, but if you're even more adventurous, you may get the diaphragmatic electromyogram and use that as an index of the drive to breathe. And there may be possibly others. Now, what about the computer algorithms to serve as controllers? Because this is really where much of the challenge is. In other words, once we've got this information coming from the patient, how do we sensibly decide how to use that, integrate it all together to decide how to drive a ventilator? Well, it's complicated because respiratory failure has many causes. It can be neuromuscular failure, or loss of central drive, or some kind of mechanical compromise, like some major obstruction in the airways. So the ventilatory control algorithm obviously needs to be specific and tailored to the underlying pathology. For example, if you had a case of diaphragmatic weakness, but the electroneurogram was still okay, then you might be able to use a measure of that to drive a ventilator. On the other hand, if you had loss of central drive, the electroneurogram wouldn't do you any good, so you'd have to use something like end-tidal PCO2 as a signal on which to decide whether you'd been ventilating appropriately or not. Now, once you've got this kind of information, how do you go through the decision-making process to drive a ventilator? Well, there's various types of possibilities. Most clinical or medical decision-making is based on empirical rules that use Boolean-type decision-making that involve if, and, then, else. So, in other words, and I've just made this up, so don't take any notice of it in the details, but if PCO2 is less than 50 and peak airway pressure is greater than 25, then peak can be increased to 15. Else, if PCO2 is greater than 50 and peak must be blah, 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 blah. And this can get very, very complicated. You can have huge, great, long lines of all sorts of complicated conditions. Now, a lot of protocols are based on that kind of structure. The trouble is that they can, as I said, get very complicated. And they're also not easily generalizable. They involve sharp transitions between decisions. In other words, if PCO2 is less than 50, do this, and if it's greater than 50, do that, and this and that may be completely different. And once you set this up for one particular situation, it may be very difficult to generalize it to another different situation. Now, something that I've worked on a bit, which I think has a lot of promise in this area, and some other work has been done on it, but there's much to do, is algorithms based on fuzzy logic. As I say, there's been some recent studies in ICU decision-making, not just in ventilatory control, but I myself have also looked at the issue of controlling fluid delivery in patients, and other people have as well. I'll explain a bit more about fuzzy logic in just a second, but the point about it is that it's reminiscent of human decision-making. So, because when we make decisions as humans, if you're a clinician and you're looking at your patient, you don't say, well, you know, if it's above 50, I'm going to do that, and it's below 50, I'm going to do such and such else, unless you're following a specific protocol. You tend to look at it and say, well, it's about right, it's a little bit high, it's a little bit low, I'm going to turn it up a bit, I'm going to turn it down a bit. So some kind of an algorithm which captures that capability might have a lot of advantages. Now, if you're not careful, these algorithms can get complicated, and the best way to implement them is often not apparent. And a final type of algorithm, which is the one that the engineers always try and get if they can, and this is frequently not possible in medical situations, is if you actually have a mathematical equation which describes what's going on. And here we have a mathematical equation which says that the pressure of the respiratory muscles ought to be 7.4 times the difference between PCO2 minus 45 plus blah, blah, blah. You can see that. Now, don't write that down because I just made it up. I just made up a fancy-looking equation. But let's say some clever physiologist had gone into the lab and found that that indeed was the appropriate equation. Well, then the problem would be solved, because you'd simply measure PCO2 and PPI and PO2, and you'd put it into that equation, and then you'd feed that straight into your ventilator and say, generate that muscular pressure, like that. The trouble is, we don't have such a formula, which is a shame, and we're very unlikely to get one. So I think that's a pretty hopeless way to go. Now, finally, let me just say a little bit more about this fuzzy logic business. I'm going to do this in a very general, hand-waving way. I have worked on a prototype algorithm that might possibly be used to control pressure support ventilation. And the idea about fuzzy logic is, let's see if I can get this. Here it is. Okay. What you do in fuzzy logic is you look at the variables that you're measuring, and in this case, we're talking about tidal volume, heart rate, respiratory rate is changing with time, respiratory rate itself, SaO2 is a percent, and the rate of change of SaO2. And you look at all those variables over their range of possible values. So in the case of heart rate, we're considering heart rates from 40 up to 150. And in this case, we've divided that range of heart rate into 3 sets, which we call low, okay, and high. Because obviously a heart rate of 150 is high, a heart rate of 40 is low, and a heart rate of about 80 is pretty good. But who would like to say, well, I'm going to make a sharp cutoff where below it's definitely low and above it's definitely okay? You can't do that. So what fuzzy logic does is divide this range into overlapping sets. So the okay set, you see, starts off having a membership of 0 at what I've got here, at 50 beats per minute. And then as we go up towards 70 beats a minute, we get more and more certain that that's an okay heart rate. Once we're between 70 and 100, we're sure it's an okay heart rate, so we have a set membership of 1. And then as we go up here, we get less and less certain that it's okay, and more certain that it's high. And so we do that with all the variables that we're measuring. And then we have a rule table that says, if the heart rate is high and the respiratory rate is low, and the SaO2 is okay, then turn the ventilator up a bit or turn it down a bit. You make a rule table. So we end up with a structure, the algorithm that we used took the tidal volume, heart rate, respiratory rate, and O2 sat, and the rates of change of heart rate, of respiratory rate and O2 sat. And from that came up with 2 quantities which we defined as the patient condition and the trend in the patient condition through a set of rule tables. And through a subsequent rule table, we then came up with a specific recommendation for how the level of pressure support should be changed. Now, I haven't been adventurous enough to actually try this prospectively in patients yet, but we did try it retrospectively in data, and it looked like the algorithm behaved itself pretty well. So I think there's some future for that. And the final thing, of course, is that if you are going to implement a automatic control algorithm like that, you're going to have to need a ventilator which is capable of responding sufficiently rapidly to these changes in commands. And it could well be that we need a new generation of ventilators ultimately to do this. So in conclusion, automating ventilation means closing the loop. In fact, we're always closing the loop when we ventilate, even if a physician is doing it. But what we really mean is closing the loop without any human interaction. We're far from doing that yet. Devising a suitable control algorithm is a major challenge, and I would like to suggest that fuzzy logic is a promising way to go. There's a lot more we can do with currently available sensors. I think the sensors we have at the moment may suffice, at least for the first pass at this problem. And as I say, we may need more flexible ventilators that can be computer programmed and have the flexibility to respond to these ever-changing commands that we're eventually going to generate. Thank you.
Yes. Any question for the audience? Please. Sorry.
Jason, I'm not very good at PAV, that's for true, but isn't there an algorithm in PAV that you must have to set a gain to? Like you say, it's always like it's flow times a constant, but I mean, if the constant is the resistance and the constant is the elastance, then you would have flow times, is that 100% unloading of the lung and chest wall, or is it like 50%?
Oh, yes, you're right. I mean, normally in PAV you would say, I think this patient needs 50% of its elastance unloaded, if its elastance unloaded. That means you have to know what the elastance is. And what if the elastance changes? You need to be able to measure the changing elastance on the fly. And my point is that that's difficult to do while you're implementing PAV. You have to stop the PAV and do some special maneuver in order to do it, so it's a bit awkward.
No, I follow that, but the thing about making a closed-loop system to me is then that what you close in here is that you are percentage-wise unloading the respiratory system of its load. Doesn't mean that you keep anybody comfortable, because the drive might change completely if the respiratory muscle function is altered. This wouldn't do anything for that.
Oh, yeah, sure, absolutely. So, I mean, it was a fairly contrived example. You might need to have some index of patient comfort or muscle function, and if that's changing, build that into the controller as well. Yes, quite agree.
Any more questions?